This video will cover Chapter 1, Section 1 in your textbook. So before you start this video, please go back and read through that section. So this section in your book gives you a great crash course of different definitions and kind of the overall history of chemistry. So chemistry, as we know it, is the study of the composition, properties, and transformations, or fancy word for changes, of matter. So the biggest thing is that it is an experimental science. So we fall back on the scientific method, which follows the pattern of you make observations and you do some experiments. You have a hypothesis or kind of a working theory. Then you keep testing and keep experimenting. And if your hypothesis is, kind of shown to be true as you keep testing and other people around the world test that same hypothesis and get to the same results, you have the workings of a scientific theory. Now, if at any point something kind of disproves your hypothesis, you just kind of go back, change it around a little bit, and keep testing. So a theory is defined as just an explanation or model of some natural phenomena. You can be capable of predicting future behavior, but you still test it. Right? So the kind of core principle behind this is that you keep testing and testing and testing. The history of this subject matter dates all the way back to ancient Greek philosophers. They spent a lot of their time thinking about the ideal universe and ideal behavior and tried to rationalize what they saw through the lens of, reason. Your book highlights atomism, which is the belief that all forms of matter are composed of extremely tiny, indestructible building blocks called atoms. Now, obviously, the Greeks didn't have, the technology necessary to test this theory. But based on what they observed, was their general idea. Now, the big difference between scientific theory and this kind of natural philosophy is that scientists strive to develop theories that are concise and testable. All right, the biggest thing here is that they need to be testable, so we can understand the universe through empirical knowledge gained through observation and experimentation. So as scientists around the world practice the scientific theory, they may be testing similar observations and they may come up with very similar results. So after many, many rounds of testing and repeated observations and experimentations, people might reveal consistent patterns and relationships, and then you can kind of gather these and make what's called a scientific law. So a scientific law is a concise statement of a fundamental scientific principle. So it summarizes past observations and can also help kind of predict what will happen in the future in a similar situation. So scientific laws explain and kind of describe what is happening. So they describe natural phenomena and, the relationships there. But scientific theories explain why those things happen. So you have a law to tell you kind of what's going on and a theory to tell you why that is happening. So again, these always harken back and start with the hypothesis. So you see some things, you kind of make an educated guess as to what is happening. And the biggest thing about a hypothesis is that it needs to be testable. So you continue to experiment and test your hypothesis. And as you continue to test, you get good data back. It strengthens your hypothesis. Other people are able to test it as well. And all of this kind of, joins in together, and the hypothesis might be elevated to the rank of a scientific theory. So we're going to throw it way on back, go to ancient Greece with Democritus around 460 BC, so way, way back. And he posited that matter is composed of indivisible atoms that are in constant motion, moving through empty space. And they differ in size, shape, and mass. Now again, this was just based on his observations. They didn't have the technology available to test this. So Aristotle, a little bit later, said that matter is composed of 4 elements: earth, air, fire, and water. And then this was the predominating theory for about 2,000 years. So we kind of just took what Aristotle said and kind of ran with it. So now we're going to flash forward to the 1700s. We're going to talk about a French chemist named Lavoisier. He actually your book mentions that he published the first modern chemistry textbook, so you have a lot to either thank him or maybe curse him. But he stated that mass is conserved in chemical changes. So this is our what we call the law of conservation of matter. It states that matter can neither be created nor destroyed within chemical reactions. And he also posited that the reactant mass is equal to the product mass. Now this might include some unreacted reactants, kind of a weird way to say that. But this formulates what we call the law of conservation of matter. Lavoisier also had a book that contained a list of substances that he thought couldn't be separated into simpler substances. So we call these things today elements, and we're going to learn more about those in chapter 2. So a little preview. So around this time, a lot of scientists were experimenting with how elements combine together to form things that we now call compounds. Proust was another French chemist who did some work with combining different metals with oxygen. And through his experimentation, he determined that the compounds that he made always contain the same proportions of their component elements. All right. So he called this the law of definite proportions. So essentially, like if I get a sample of pure water from Clemson, and then from Los Angeles, and from Moscow, and maybe Cape Town, if it's all pure water, it's all going to have 1 oxygen and 2 hydrogens. It's going to have the same composition, regardless of the source. In the early 1800s, John Dalton did a lot of work in this area as well, and he came up with what is now called the law of multiple proportions. So this builds on Prost's work. So what Dalton found is that if you have 2 elements that can form more than 1 compound between them, the ratios of the masses of the second element, which combine with the fixed mass of the first element, will be ratios of a small whole number. So this kind of alludes to chemical formulas that, again, we're going to talk about in later chapters. But for example, your book talks about tin and oxygen. So tin and oxygen can combine with one another in a 1-to-1 ratio. So like 1 tin atom and 1 oxygen atom. And it can also form, for 1 tin atom, you can have 2 oxygen atoms. But it will always be a whole number ratio. So you're not going to find that it's going to be a half of a tin atom for a whole oxygen atom. They're all going to be whole numbers. So in 1808, Dalton came up with the atomic theory, and that was based on 2 laws, the law of conservation of mass and the law of constant composition, so the 2 that we've talked about. So the first part of this atomic theory states that the smallest identifiable unit of an element is an atom. So again, while this tracked with his technology at the time, we have learned since then that within an atom, we've got protons, neutrons, and electrons, these subatomic particles. So we do have things that are smaller than the atom. The second part states that each element has a unique atomic mass, and that different elements have atoms with different masses. Now this is partly true. We know that a sodium atom weighs more than a carbon atom, so they do have different masses. But since then we've learned about the presence of isotopes, which have the same number of protons, which is one of those subatomic particles we'll talk about in the next chapter or 2. But they have different numbers of neutrons. So even though they have a different mass, they're still the same atom, it's just a different isotope. But we'll get into more detail with that later. The third part is that elements combine in small whole number ratios to make different substances. So again, we know this to be true. If we have water, H2O, we've got 2 hydrogens and 1 oxygen coming together. We're not going to have like 1.5 oxygens coming together with some other fraction of hydrogen. We have whole atoms. The last part is that in a chemical reaction, atoms are unchanged. So they're only rearranged. So they just do a little do-si-do, a little swing dance, and come out with another partner on the other side. In traditional chemical reactions, this still holds true. Nuclear reactions are an exception to this. You can generate new atoms through nuclear reactions, but again, we'll talk about that later. So again, nowadays we have really powerful atomic microscopes that can, effectively allow you to visualize single atoms. So shown here is a picture with the purple arrow pointing to it of silicon atoms on a silicon wafer. But again, the things that we see are pretty much consistent with Dalton's atomic theory. So even back in the early 1800s, they were able to make good laws, good theories that tracked well with time.